Alright everybody, we're going to look at Unit 18. This is problem solving. The main topics of this unit are going to be the following. So basically we're looking at a rate times a quantity is going to be another quantity. Distance equals rate times time, and of course mixture problems. In particular we're going to look at percent mixture problems. Alright, so jumping right into this one here. So the first idea here is we're basically going to go over the formula for cost. And so if looking at the example here, it talks basically about the amount in ounces and how that cost increases. So for example, 1 unit of this in ounces is equal to 8250. So 1 times 8250 is going to be 8250, clearly. 2 times 8250 is going to be $165. Okay. 3 times 8250 is going to be $247.50, right? And then you would just continue in this fashion, right? 4 times 8250 is going to be whatever it is, and the same thing here, it's 5 times 8250. And that gives us that amount that goes in these respective boxes here. So basically what is happening here, so what you do is you're taking the amount, okay? And you're multiplying that amount times the price per unit, and that's going to give us the total cost. Okay? So the amount times the price per unit, that's going to give us the total cost. That's one of the formulas here. But essentially, this is one of those rate times quantity is going to be another quantity one. Okay? So essentially here on the next table, they continue to talk about it over here. And this chart is basically an organizational structure, and it is essentially already doing and writing down what we talked about here. It was the times 8250 and then the 5 times 8250. You should fill these in and get these values here. At the bottom here, we're talking about the amount. We have the cost per unit, and we have the total cost. So the formula is amount times the cost per unit is going to be the total cost. The simplified version of this is A times C equals T. Again, the amount times some rate. This C is the rate of percentage. This is going to be my final one. The same thing is true if we're mixing, the mixture formula for percentages here. In this little example here, it talks about Mia. She's going to make some lemonade. It has water, sugar, lemon juice, all this stuff. There's a bunch of percentages happening here. The recipe states that 35% is lemonade, must be made with lemon juice, 25% sugar, 40% is water. She follows the recipe. She makes 6 gallons of lemonade. Her friend asks her, how much lemon juice did you use? Well, I don't know. Well, let's figure it out. So how would we do this? Well, she wanted to know over here, notice 35% of the lemonade is lemon juice. And so basically, and the total was, there was 6 gallons of lemonade. So what does that mean? So basically, we need 35% of 6 gallons. Essentially here. And notice over here, so what we have is 35% is going to be 0.35. From 2 quarters ago, we should remember how to convert a percent to a decimal. And then that is gallons of lemon juice per 1 gallon of lemonade multiplied by 6 gallons. So we were to multiply it out. Notice over here, you can multiply by gallons of lemonade. The gallons cancel out. Notice you get a 1. And what we get is 0.35 times 6 gallons of lemon juice, which gives us over here this calculation. So we have 2.1 gallons of lemon juice in the 6 gallons. So what is basically this saying here? So what you could do is you want to think of this as the following. If you're taking the percent concentration, or I'm going to abbreviate this as percent times some amount or some number, you get the amount of ingredients. Here, okay? And this formula is highlighted basically over here. Again, percent concentration times amount of solution is the amount of ingredients here. I sometimes like to shorthand this as my percent times some amount 1 equals my amount number 2, depending upon what you're looking for. But if you notice, it's again the same kind of thing. The same thing here, motion. We have d equals rt, that is, distance is equal to rate times the time. So if you give me a rate and a time, I can give you a distance. Vice versa, if you give me a distance and time, I can solve to find the rate. Okay. In this example, it talks about that here. I'm not going to go over it though. You should read this one over though. Notice over here, all this chart is basically talking about the time and traveling over here a certain distance. And so from this, we can kind of get an idea. But we're going to go ahead and move forward with this one. The main thing we want to focus in on is the distance equals rate times time formulas here. You should fill these in, look back on the notes, and fill in what these formulas mean in their words, just to remind yourself. Okay? We already went over this one. Over here, with getting familiar with the formulas, basically these next examples are this very simple applications of A times C equals T, P times S equals I, and then D equals RT. Okay, so all of these are applications of those. They're really fairly straightforward. Just one quick step simplification. Okay, I'm not going to go over these because they're fairly simplistic. For the classwork here, you should really, just to test yourself, you should work on A, you should work on C, okay, and then you should work on D. Okay, again, these are fairly straightforward. They're not that bad. You should work on them just to test your own knowledge. All right. The bulk of what we're going to be looking at here is solving our motion mixture problems. Okay. If we remember, we have the 4 different kinds of cases here. Okay, so we're going to remember this right now. So here we have case 1. So this is solving. So this is D equals RT. If you forgot this or don't know, please write it down. So we have a case 1. In solving these kinds of problems, you have the case where 2 objects, like they could be cars, they could be runners, they could be whatever, are colliding. Each of them gets a D equals RT for every path. Okay, they get a D equals RT, and these are different ones. So I'm going to call them sub 1, sub 2, sub 2. That's case 1 here. Okay, distance equals rate times time. Another one, let's call this case 2. You have somebody going out, and then they have to come back here. So notice this one path, maybe they're going out over here to a shack or something like that, or a house or whatnot, whatever the story is. Each path out gets its own distance equals RT. Okay, and then coming back also gets its distance equals RT. The key thing to remember in this case 2 is the distance out equals the distance back. So in this case, D1 is D2, right? Because if I go out, I come back, it's the same distance here. We want to look, so case 3. For case 3, we have somebody's head out, maybe it's a plane that's left, and then another plane is heading out to try and catch this plane. Okay, and again, for each path, each one gets its own distance equals rate times time. Each one here gets its own distance equals rate times time. Okay, and then we want to go ahead and solve these ones, and we'll look at that. And the last case is going to be when we have 2 things. Let's do case number 4. So case 4 is when we have 2 objects and they're going away from each other. Okay, maybe it's a car, maybe there's some trains, it's a locomotive of some kind. Okay, it's on some tracks and they're going away from each other, but each of them here gets their own distance equals rate times time. Distance equals rate times time. 1, 1, 1. 2, 2, 2. Okay, and typically with these ones, they like to give you the distance. They'll give you the total distance here. This is the total distance apart, and that is given by D1 plus D2. Okay, so these are the four kinds of distance equals rate times time problems, and this is the kinds we're going to solve over here. So example number 5. if you look at it here, it says the BART, basically, has many stations where the trains are constantly entering and leaving. Suppose the two trains leave at the same time from Fruitvale Station. The first train is traveling north towards Richmond, and the second train is traveling south towards Fremont. The southbound train is leaving at a rate of 6 miles per hour slower than the northbound train. In half an hour, the two trains are 45 minutes apart. Find the speed of each train. So just to clarify, when you read this, you should read this at least 3 times. Okay? So how do we solve this problem here? Well, the first thing we need to figure out is which case do we have? Okay? So what are our cases here? Remember our 4 different kinds of cases. So what's happening? I have a couple of BART trains. What are they doing? Are they going towards each other? Are they going away from each other? So they're leaving at the same time from the Fruitvale Station. So like the center would be, here's Fruitvale. I'm going to draw a picture because that's important for me. So here's Fruitvale. The first train is heading north towards Richmond. So I'm going to have maybe one going upwards here. Okay? And again, look, I have a path, so that gets a D equals RT automatically. Now I'm automatically just going to put it there. The next one, the second train is traveling south towards Fremont. So here, it's going to go south here. And this path gets its own D equals RT again. So it looks like we have the case where they're going away from each other. Okay, it's kind of like this. The southbound train is traveling at a rate 6 miles per hour slower. So here's the key word. The key word in this is, if you notice, is slower, right? So who's going slower? The southbound train is going slower. So this person's rate is slower than that person's rate. So if the key thing to not do is not call this 6. This is not 6 here. It's not 6. Why? Because it's 6 slower. So for example, let's just say that this BART's train's rate is 10. This one would have to be what? It's 6 less, so that would be 4. Let's just say this one's rate was 25. Then this rate would have to be what? It would have to be 6 less, so it's 19. Okay? So whatever it is, it's less than that. Okay? So we don't know what it is. We call this R1, and those are R2 over here. But we'll get to that later. So in half an hour, the two trains are 45 miles apart. So notice here, this total distance we know it is 45. So that's 45. And what else do we know? We want the speed of each train. Okay. Well, what else do we know? We do know the what? The distance between both of them is 45 miles. Okay. The rates we still don't know the rates. Well, we know that one of them is slower than the other one. Okay. And we do know the time, right? The time is in half an hour. And if you notice, they left at the same time. So what does that mean? That means that T is half an hour, or it's going to be 0.5. Or a half, whichever. So T is 0.5 here. What else do we know? We're trying to find the rate. So if I call this rate X here, then this rate is going to have to be 6 less than that. So it's going to be X minus 6. Okay? Alright. So then, what else do I know? I know that this distance plus this distance here, if we remember, D1 plus D2 is going to be the total distance. So what's the total distance? The total distance is what? It's going to be 45. D1 is equal to X times 0.5 plus D2 is X minus 6 times 0.5. And we get 45 here. And this is so this is the setup for the problem here. That's the basic walkthrough. This was done earlier. And we essentially can kind of map and walk through this every single time in the same way. If you look on the next page, this is a nice little chart that's set up here. This chart can also be used. It's sometimes very helpful, right? So you write in your rate, which you're trying to find, call that X. You can call this X minus 6. Note, alternatively, if you had called this X, you would have called this X plus 6. Why? Because no matter what distance, whatever rate this is traveling, This is traveling 6 less. If you have x plus 6, if you subtract 6, you get x. If that's confusing, just ignore what I said. But anyways, you can set it up in the following manner over here, and that one's done. Make sure to solve this one over here. So go ahead and solve that equation, and then you'll get your answer. Make sure to answer for both of them. In other words, I want the speed of train 1 and train 2, or the northbound and the southbound one. Okay? So make sure we answer the complete question. All right. Example number 6 here. It says, our Numfo went on a short hike with his friends. They hiked up a hill at a steady pace of 1.5 miles per hour. Once they reached the top, they decided to hike back down the hill, back down the same path. They were able to hike downhill at a faster pace of 4 miles per hour. So I'm just going to underline the key word here, faster. So that means more, okay? Also, what else we have? That was a steady pace. Okay, that was another number. If the time it took to climb the hill took an hour longer than the time it took to hike downhill, how long was the entire hike? Okay, so what's happening here? Which of our cases do we have? Do we have things going away from each other? Do we have things going towards each other? Do we have a loop happening? Is somebody trying to catch up? Is this like the last problem? So go ahead and take your best guess. Which one is it? And if you guessed it, it's going to be case number 2. So this is case 2. Why? Because you're going up the hill. You're going up the hill and you're also coming back down. Okay? So again, each of our paths, we're going to give a distance equals rate times time. This gets a distance equals rate times time. 1, 2, 2, 2. Okay? Alright, so we just have to fill this in with some of this information. The hardest part is filling in the information. Right? So what's happening? They hiked up the hill. So let's call this we're going to call this up the hill, and we're going to call this one down the hill. Okay? So I go up the hill and I come back down. A steady pace of 1.5 miles per hour. So that's my rate. So over here, going up the hill, that's 1.5. All right, that's done. Once they reach the top, they decide to hike back down on the same path. They were able to hike downhill faster at a pace of 4 miles per hour. So on the hike back, they did it at 4 miles per hour. If the time it took to climb the hill was an hour longer than the time it took to hike downhill. Okay? So in other words, so I don't know right now what the times are. And if you remember from case 2, the cool thing here, the distances are equal. So we know that D1 is equal to D2. So what do we do now? Well, we want to find how long was the entire hike. So we want to find T here, right? Or T. Whichever those T's we want to find. So we want to find the time. Okay? So we need to give a generic variable to either this T or T1 or T2, i.e. we want to call X T1 or we want to call X T2. Which one? Well, it doesn't really matter, but let's go ahead and pick one. So if we notice here, if the time it took to climb the hill was an hour, if the time it took to climb the hill took an hour longer than the time it took to hike downhill. So for example, this hike up took longer. Right? So this time here was longer than this time. Okay? How much longer? It was 1 hour longer. So if I call this here X, this would have to be X plus 1. Okay? Why? Because whatever time this is, this has to be more than that time here. So then what? I know now that D1 equals 1.5. Let me see. 1.5 times X plus 1. Similarly, D2 equals 4 times X. So, and I know that D1 is D2, so then I get 1.5 times X plus 1 equals 4X, and then we solve that, and we're done. Okay? On the next page here, you can see that again we have a nice little chart setting it up. Okay, this chart is, again, some people really like the chart. Okay, You fill in your respective ideas. So we're going up the hill and we're going down the hill. We have the rates. We know the times. Notice, you could have also, if you wanted to, if you had called this t, this would be then t minus 1. Why? Because it's less. This one took less time. So you could have also called it this, and you would have solved it and got the same answer. So notice over here, it's solved out over here. And then once you find your t, this is not the answer, because if you notice the question asked, how long was the entire hike over here? So what does that mean? In other words, this was the time it took to do what? To go down the hill. So it's going to be 1 plus that. So the time up the hill plus time downhill equals total. So up the hill, that's was 1 plus t, so it's going to be 1.6 plus 0.6, excuse me, which is going to be what? What is that one? Was it 2.2 miles, right? Is that correct? So that gives us the total time. And this is in hours. So we should say 2.2 hours here. Okay? Okay. Example number 7. So 2 planes leave SFO at different times. Okay? The smaller plane leaves at 7 a.m. This is their rate. And the larger plane leaves 2 hours later, and this is their rate. Both planes are headed in the same destination. Clearly, this is a picture of I'm trying to catch up. I even have the planes there. So each one gets a D equals R times T. D equals R times T. Okay? And we just fill it in. So the smaller plane leaves at 7 a.m. and their rate is 340 miles per hour. So you have to kind of figure out which is which. Okay, so I have the smaller plane and the bigger plane. So which one is which one? Well, who left first? It says the smaller plane leaves at 7, and then the larger plane leaves 2 hours later. If I leave 2 hours later, then you left before me. So let's just call this one the small plane here. Let's just call this the large plane. Maybe you can see by the picture, but I just want to be really clear. Okay? So now what? So the small plane, the rate is 340 miles per hour. So that's their R. So it's 340 here. The larger plane leaves 2 hours later. So I don't know the time, but it's going to be 2 hours less than this one, right? Because this plane had 2 hours more traveling time. So this plane had 2 hours less traveling time than that plane. Okay? And then the larger plane leaves 2 hours later, and their rate is 500 miles per hour. So this rate is 500 here. Okay? And then it says both planes are headed to the same destination. What time will the large plane catch up to the small plane? Notice when it says catch up, write this down. When they catch up, the distances are the same. Right? So in other words, i.e., if this eventually, when they meet each other, their distances are going to be equal. I.e., the D1 is going to be equal to D2 when that happens. So we're going to use this fact here at the end. So D1 is going to be equal to D2. So then what do? We just need to figure out the times. So again, we're going to call one of them X, and the other one is going to be something else. So which one should we call X? Well, let's see. So again, the smaller plane leaves before the larger one, and the smaller plane has 2 more hours traveling time. So we have options. So the time is either going to be X, and this is going to be X plus 2, or this is going to be X plus 2, and this is going to be X. Okay? So think about which one it's going to be. Let's think about it. Which one is it going to be? Okay. Hopefully, after thinking it through, you should pause it and think before you move on. Because this has 2 more hours, we're going to call this x plus 2, and then this will just have x on it. Okay? So hopefully that makes a little more sense because this has 2 more hours traveling time than this one here. And when they catch up, D1 is D2, so what does that mean? That means that, so when they catch up, D1 is D2. What does that mean? So I have 340 times x plus 2 is going to be equal to 500 times x. And then now you just solve this. Okay? And then that will give you x. What is x? X is the time. Note here, x is, that's the time for which one? For the large plane. For the large plane. Okay? And notice over here, this talks about the time and t plus 2 being the smaller time, etc. And again, here we have our nice little chart filled out. Okay. Again, sometimes some people really like the chart. Maybe you do. Okay, maybe we'll have some blank ones for you. Okay. And you should solve this one out. And if you do, lo and behold, it's over here. You get t equals 4.25. So that's the amount of time it takes for them to catch up. All right. This is a discussion one. We're going to skip this one for now. So we're going to skip. Okay. Lastly, we have a collision. Again, a collision. Each path gets its own d equals rt. Automatically, you should just do this immediately, just to remind yourself what you have to fill in. Each one gets its distance equals rate times time. Put a little spot there to kind of separate them. Apparently, they're going to be some distance apart. So it looks like we have Percival and Fabian live on opposite sides of town. There's a path. Can we see this? Excuse me. There's a path that connects Percival's house directly to Fabian's house. The total distance of this path between their houses is 96 kilometers. Both friends decide to bike on this path starting from their respective houses at the same time. In order to meet up and check their answers on their math homework, Percival can cycle at a steady pace. Okay, so all of that was kind of excess information. Steady pace of 10 kilometers per hour. Fabian can cycle at a pace of 14 kilometers per hour. So, and again, so notice this is already labeled here, so we're going to fill this in as we go. So Percival can cycle at 10 kilometers per hour. So this is the rate because it's per hour. So this one here is going to be 10. And Fabian can do it in 14. Okay? So I'm just filling those in. After how many hours will Percival and Fabian be able to exchange their homework assignments, right? So that is, how long will it take for them to meet up? So when will they meet? Well, in this case here, we know what fact? We know that D1 plus D2 must be 96 in total. Okay? What else do we know? Do we know anything about their time? What does it say about their time? It says they leave at the same time. So what do we do in this case? Well, we don't really know. So if they leave at the same time, what does that mean? So, i.e., in the other problems we had, someone left before or later. So that means they had added or subtracted time. Because they left at the same time. So here's the thing. The key word is, where is it?